So it's our pleasure today to have Allan Sapucaia from University of Campinas visiting. He'll tell us about solving geometric problems, combinatorial optimization in general. And so without further ado, please.
Thank you for having me, Jacob. So today I'm going to talk about a problem that I'm working on right now. So this is work in progress-ish. We are writing it. There's something that a little bit convoluted, but we are getting there. But I think it illustrates the work that we are doing there in our research group that is combining operations research techniques to solve hard computational geometry problems. And this is joint work with my advisors, Professor Teresa Souza and Professor Siri from Toronto. I'm going to start by explaining the problem that we are going to go through. It has very large name, minimum recallable discrete unit discover. We are not going to say that again, but let's break it down. It's a geometric problem in the plane. It has as input a point set that we want to cover and a set of disks that are going to be used to do the covering. And the idea is to model wireless network where we have clients represented by points and antennas available, and we want to minimize the number of antennas that we are going to install so that all clients are served. However, we're considering a constraint on the signal. It is known in wireless networks by IEEE standards that routers can reasonably do 3 frequencies. Otherwise, the quality of the signal might deteriorate. And we want the antennas that have the same frequency don't overlap, because the overlap can lead to destructive signals and the connection lose quality. So the problems, we want to cover those clients, they're represented by points, and the antennas represented as disks. But we are going to color those antennas using 3 colors. And our goal is that we want to minimize antennas, and we don't want antennas assigned the same frequency or color to overlap. So we have a set of colors that we have 3, so it's luckily RGB. And here is what a solution to an instance of this problem look like. So we have those points, they are the clients. Here I'm not showing all the disks. I think the system has like 100,000 of possible antennas. And this is a solution. It has, I think 8 antennas, and we managed to install them following the coloring so that we avoid disruptive signals. All clients are served, all of them are happy with their connection quality.
But Allan, we would not be happy with 2 red circles overlapping, for instance.
No, because that might mean that someone might miss some package and they need to resend that. That means the quality of the connection is going to drop.
One question, what if it overlaps but there's no points in the overlap?
So in this case, we are assuming that might lead to destructive signal because the signal might get overlap, and when it gets to those clients, it might be destructive. So they don't need to be on the overlap. The signal might be destroyed in between the clients, so they still have package loss even if they are not covered by the overlap.
Do you want to move the pictures somehow?
Okay, yeah, let me just probably remove them. Yeah. So yeah, this is rather small. Let me just move this somewhere. Yeah, thank you. I didn't notice that. So this is actually a small-ish instance. We have 500 points, and our candidates were 5,000 disks or antennas, and we picked those because they are two-colorable and they minimize our objective function. This is an instance where the antennas are really big, but there are instances where it's not that case. So to review, this optimization version where we want to minimize the antennas is something that we are proposing because, well, the literature has a decision version where we are asked, is it possible to cover them using two-colorable disk sets? And since we are using interlinear programming, we kind of get an objective function for free. So we're trying to minimize that. And that decision problem is NP hard. As specified here, it was published in 2021. And there are 2 approximation algorithms what the literature has in terms of solving it. And they have a factor of 2. That means that they might use 6 colors since they don't have the same objective function. they are allowed to try to fit into 3 colors, but they might need to use 6. And what happens is they have a very prohibitive cost. The n is the number of points, n is the number of disks. So even the fastest one has m to the 18th. So it's not possible to solve any meaningful fractal instance with these algorithms. They did work by splitting the space and trying to solve small instances in polynomial time by search. That's why the coefficients are so high. And then they combined those separate stripes in this case of this fastest algorithm. And they show that by combining, they might double the number of colors, but they solved optimality strips that are easy to solve. And just one thing that I forgot to mention, I think I read, but those are units. That means that they have the same size, and we can scale the instance to make it to be 1. So all antennas have the same range. And there are a lot of different problem literature that captures some aspect of it. Like the tricolorability appears a lot in wireless network designs, but sometimes it's not using the geometry to model the antenna. Sometimes they just measure signal and create a graph. But here we are using the full geometric description of the problem. And well, let's write our first model for it. And to do this, we are going to create binary variables x, dc, where d is a disk and c is a color. And that variable is going to be 1 if we are going to use that disk, install the antenna, and assign the frequency corresponding to the color c. So with that, we can express the model as, well, we want to minimize the antenna that we use. We don't care about the colors in this part, so we just sum over our axis. And we can do coverage just by looking, okay, given a point, what are the antennas that cover it? At least one of them has to be installed, doesn't matter the color. These are the first 2 constraints, the first constraint and the object function. We are just missing coloring, and I'm going to introduce probably my favorite structure in computational geometry, the arrangement. The arrangement is a very simple idea, at least in the plane. You have a set of objects, in this case are circles, and you just draw them in the plane. It's going to give you a planar subdivision. So here you have 5 disks. We have a unbounded face that is the outside of all those disks. Then we have E, it covers its own face. And then we have a bunch of overlaps there. Each one of those regions in the plane is a face in the arrangement. It is very efficiently constructed. The fact that these are quadratic curves makes it a little bit harder, but it is done. The SIGO library has a very good implementation for it. And that gives us a good partition of the plane with respect to each face is covered, each point in a given face is covered by the same disks. So if you want to add constraints about not allowing this to overlap, we just, for each face, we pick a point and we say, okay, for this point, all disks that cover it, we have to have 1 for each color at most. So 3 constraints, 1 for each color, determine that a point is covered by at most 1 of them, and we can limit ourselves to the face in this arrangement, which are the worst case quadratic. So which means that they are atomic with respect to covering.
And the antenna placement is fixed.
It's fixed. It's a discrete version of this problem. There are variations where you are free to choose where you're going to install this antenna. Here we assume that we already have pre-selected positions where they're going to be installed.
Because that was how the constraints on the previous slide could be so simple. Like you know where the antenna is, and then you just can see if it's serving a point.
Exactly. In this problem, the antennas are given as a set in the beginning, as are the clients. And we want to pick among. There are versions where you're free to choose where you're going to place this antenna, but this is not what we are going to focus today. And with the arrangement, we can construct our first full model. So again, object function, we want to minimize the number of antennas we are installing. For each point, we look at the disks that cover it and say that we have at least 1, doesn't matter the color. And finally, the coloring comes from 2C for each one point representing a face. So we pick a point for each face. And for each color, we want to pick at most 1 of the disks that cover it. And finally, our variables are binary. And we're going to, from now on, we're going to look at this model, see what it does, what are the bottlenecks, how to address it, and move on. So for this particular model, as it is probably the simplest one of the simplest ways to express this problem, we could solve up to 700 disks. And then we start to run into issues with the construction of the arrangement. Arrangements are very powerful structure. They usually, when you want to start a model for a computational geometry problem, you start the arrangement, but they usually don't scale very well. They have too much information. So successful applications of arrangement usually do something about it. Don't construct it entirely, or just use it to prove correctness and then start doing other things. So at this point, the arrangement is our bottleneck. The points don't matter much, but we cannot go over 700 disks. And well, the first approach to do this is a very common one in operations research, which is lazy constraints. Lazy constraints are a subset of your constraint that you're not adding to your model when you start. They are necessary for correctness, as opposed to cutting planes that are helpful to converge to solve faster. Lazy constraints, they are necessary for a model to be correct, but you remove them. And what changes is you do your search in interlinear programming, your bounds, your relaxation, you can do that always is still valid. However, when you find a feasible solution for the problem that you have at hand that has some constraint removed, you have to check if there's any violations. And this is a straightforward approach when you have constraints that you simply cannot enumerate or having a hard time with that. Here we could do, giving a solution, we could look pairwise which disks overlap and simply write a constraint saying, please don't take those two disks with the same color. But we can use the geometry to do something stronger. And the idea is, as we did with faces, we pick a point inside a face and write a constraint about limiting ourselves to one disk that covers that point per color. Here we can simply pick a point in the intersection of those two that were assigned the same color. And we can just do the same thing. We can write a constraint, say, okay, the two disks overlap, pick a point between them, and let's not pick two disks with the same color that cover that point. And that leaves us with constraints that are kind of the same as before of the arrangement, but we don't have to do with arrangement anymore. We check pairwise if this overlap. We can even get the arrangement for this subset of this because the solution is expected to be sparser and smaller, but pairwise here worked very well and was never a bottleneck for our approach. So we just pick the centers, pick a point in between them, and write the constraints. And well, that is enough to get over our problem with arrangements. Why we don't have arrangement anymore, they were useful, and just step back. So at worst it can do is that you can end up having to pick a point inside each face. So you cannot generate much more constraints than the size of your arrangements. You might get unlucky and hit some vertices or some arcs, but even then you are still bounded by a quadratic number of constraints to be separated. But in practice, this is much smaller. And now we went up to 3,000 disks just by doing this simple separation. And now our bottleneck, before it was memory and disks, now are points. So points are now what is more sensible about this model. So if we fix a time frame with 20 minutes, see how much we can solve. Around 500 points, things start to deteriorate performance-wise. And what we're going to do now is, again, what is happening? Lazy constraints are awesome to get your model running when it's just too large to fit in memory, but they have a cost, very large costs. When you do that, when you give your solver your partial model and say, hey, when you find a solution, I'll do something about it, it loses pretty much all preprocessing because it doesn't know the whole model. We cannot make any assumptions about it. And well, without preprocessing, solving IOPs becomes a lot harder, but again, we couldn't do it before because of memory. Now we can't, but we have this bottleneck that lazy constraints has this cost. And symmetry was not an issue before because colors can be switched. There's a cost, there's a symmetric search there going on, and it was not an issue before. Now it starts to get noticeable. And in practice, what happens is the solver simply cannot find primal solutions. They find something, they say, no, that doesn't work for me, and eventually just cannot do anymore because we had so many constraints, you gave up on preprocessing. So here things start to deteriorate. So the next step is to change the model a little bit. So before we have a set of variables that encode both coloring and covering. But now we're going to introduce a new set of variables, YD, associated with disk. That means if it is being used or not. So it doesn't care about color, it's pretty much used to represent covering. We can change our objective function now on X, on Y, it doesn't matter, but on Y it's more natural and it's going to be a little bit helpful later. And then this new model has this new linking constraint for B, where basically say you can only use a disk giving a certain color if that disk is being used. And then for C is our covering constraint rereading. Now we don't care about color, just cover the point using an antenna. We decide the color separately. And finally, the coloring, well, we cannot do that with Y. We need to use X because that is what is encoding our coloring. And this is what this new model looks like. And it has a very interesting block diagonal structure. So if we look at it, it has an object function only on Y. That doesn't matter much, but it's helpful for convergence issues. We have the linking constraint for B. There's the only part in the model where both Y and X appear. And then we have two isolated blocks, one that is covering on Y and one that is coloring on X. And we are going to use a technique called Bender's decomposition to exploit that structure so we can decompose our problem into two. We're going to deal with covering on first, and then we see what happens, try to color it. If it doesn't, we go back and do something about the model. And there is one thing here that Bender's decomposition is a very popular technique in operations research, and it is pretty much textbook when one of your set of variables is continuous. You can just turn some flags on your solver and it's going to handle that for you. There's a lot of studies about the quality of the cuts that it found, but it can be handled as a black box. Just say, okay, I want this. These are my integer variables. These are my continuous variables. Please decompose them.
Would you just remind us maybe 30 seconds was Bender decomposition is?
So yeah. So Bender's decomposition is a technique where you solve those problems separately. So you decompose your problem by the set of variables. You have one set that is your main problem, your master problem, and then some sets, one per block, that defines subproblems. Here we have one master problem that is Y, and we only have one subproblem on X. And sometimes you get lucky and you have a lot of block diagonals, so you can get a bunch of different subproblems that can be solved in parallel. It's not the case here. We only have one, but we're going to show that even then the speedup is noticeable. So what Bender's decomposition does is we solve a master problem that is restricted to our Y variables in this case. And then when we find a solution, it starts as a set cover, it doesn't have anything special. We give it to a subproblem that has to decide whether it is tricolorable or not. If it is, we are done. We can keep that solution and continue our search. Otherwise, the feasible solution needs to be cut out by a cut that is added to the master problem, saying, okay, that solution doesn't work for me. The subproblem is not happy about it. We need to find something else. And the thing about these constraints that are added to the master problem, they have to be expressed only in terms of Y. X are not on the main model anymore. So before we were doing kind of similar thing, we had constraints out of the model and we were checking them and adding them, but the variables were the same. The variables were there, the X variables were there. They're not in use in the beginning, but the model was aware of it. And we can express our cuts that way because, well, we're just removing constraints and adding them back. Here, our main model, the master problem, is only restricted to Y. So in traditional Benders, the subproblem has only continuous variables. So linear relaxation and Farkas certificate give you a cut that is, well, very, very good. There are studies to find stronger cuts, but they are good enough. And you can do this in a black box. Just turn on some flags on your solver, say, okay, this is integer, this is continuous, please separate them. And it's going to give you a solution. However, here we don't have the property. Our X variables define a NP-hard problem that is to tricolor a graph. So we cannot solve that just by simply linear relaxation. So in this version, which is called logic-based Bender's decomposition, we have to deduce our cuts by ourselves. We don't have linear relaxation duality to do that for us. And in our case, we are going to call it violation, which is a subset of disks that we say, okay, from this subset, DV, you can only pick SV disks. You cannot pick more, otherwise not recolorable. So basically, you look at a subgraph and say, okay, we cannot have more than SV vertices in here, otherwise it's not recolorable. And this is how we are going to communicate the master problem. We're going to give a solution. We're going to return a subset of this and say, okay, your solution is invalid because it has more than SV disk on this subset. The weakest thing we can do, but it can be done automatically, is you give a solution to a subproblem D prime, and you just return, okay, I don't know why, but you have to change something about D prime. I cannot specify exactly what is going on, but I'm not happy about it, flip something. And in this case, we can just say remove a disk because it's going to have to replace with something else. So we can just add this weak cut. We say, okay, remove something from the solution. It's not good because of that. So this is what the master problem looks like. Same objective function, same covering constraint, but now we are going to, over time, add this violation. So it started as a pure set cover, but over time, it gets more and more of this backing constraints. And the subproblem is completely independent. And since we are not relying on linear relaxation, we're going to find our cuts on our own. We don't have to solve it using interlinear programming at all. We can run heuristics, we can do whatever you want, as long as we can say if a solution is valid or not. So here, for instance, we use constraint programming to solve this problem instead of interlinear programming because it has better tools to handle, for instance, symmetry. So now we have a new model just dedicated to solve the subproblem. Subproblem never changes. It's going to be please tricolor this graph or say something that justify why it's not recolorable. So we can just express as constraint programming with all different constraints. Now we have ternary variables. For each disk, we have a ternary variable that says if it is red, green, or blue. We're going to try to assign colors to this disk. If we can't, we're going to say something about that, which in the worst case is, okay, I don't understand why, but please change the solution. So we use the all different constraint, which is one of the most powerful constraints in constraint programming, has very strong propagators. So now we construct a new arrangement just for the solution and do the same thing as before. We write one constraint for each face in this arrangement and say, okay, the colors for the disks that overlap here, they need to be all different. And we just feed this to a constraint programming solver, and it's going to give us back a solution. And well, this is very good, right? We managed to separate covering and coloring. We give coloring to a much stronger technique to do it, more dedicated software. So it should make things better, right? However, disconnecting the problems, the covering and the coloring, has a cost, and it can be exploited. Essentially, the master problem doesn't know what it's doing. It doesn't know anything about colors. So it might get tricked into finding horrible, horrible solutions for exponential number of times. So let's look at this small gadget here. It is, disks here are not unit disks. They have different sizes. This is just to make the picture clearer. The idea is similar for unit disks, but uses more disks. They are much more cluttered together. But this gives all the ideas necessary to explore this worst case scenario. So we have this instance. It has 8 disks. It actually has 9 disks. Some of them are fixed. If you look at the top, we have 1 point and 1 disk that cover it. Cannot do anything about it. You have to include them. The decision comes in the bottom. You have 3 disks, DC, which is the big one, DL and DR. And you either, in a minimal solution, you pick DC and both points inside DL and DR are covered, or you pick DL and DR. Obviously, just picking DC is better for the master problem because it has fewer disks. It's going to do this every time. However, if you look on the top, there's a huge overlap of 4 disks. There's a point where all 4 disks overlap, DC and the 3 on the top. And so this solution is clearly not recolorable. It requires at least 4 colors. And so 7 disks, it is feasible for the master problem, but requires 4 colors. If we switch DC for DL and DR, we have a 3-colorable solution, but it requires more disks. And doesn't matter what we do, the solutions with the 4-colorable solution is always going to be found. The solver is always going to try, okay, is this solution good? And if we glue a lot of these gadgets together, like this is a solution for 10 of them, one side by side. What happens is for each one of those 10 gadgets, we have 2 interest solutions. So in total, we have 2 to the 10th solutions that can be explored. You either pick 2 or 1 in the bottom. And only one of them is 3-colorable, this one. This is what the solver got, so it's not symmetric in terms of coloring. And it is only one of those 2 to the 10th instances. All the other ones have fewer disks, but they require 4 coloring. So if we just do as we have right now and try to solve this model as it is, it's going to cycle through all the solutions. So it is easy to exploit this exponential worst case. Of course, this construction doesn't appear a lot in practice, but it is good to be aware of that. We decompose, the solver master problem is blind to what is happening with coloring, so it can be tricked into being very, very, very slow. So this instance has around 70 disks, 90 disks, and it's so much harder than instances with hundreds of thousands of disks, because as is, we fall into the trap of exponential number of solutions having to be explored no matter what. And that is when using logic-based vendors, modeling the master problem and the subproblem is not what it is hard. The hardest part is gluing them together. We need to find ways to express tricolorability and certify that it is not tricolorable that cut more than one solution at a time. If we do as before and we just cut one solution, we might have a very bad behavior. Here, you're not going to guarantee that this is not going to happen, but at least for that instance, for every instance that we face, the number of solutions found is rather small. And the idea is, okay, I don't have a good description of 3-colorable graphs because it is an NP-hard problem. However, I know this family of graphs called odd wheels. They are composed by an odd cycle and a vertex in the center that's connected to all of them. Odd cycle requires 3 colors, so this 4th vertex is going to require 4 colors. And odd wheels are interesting for 2 reasons. First, in particular, the odd wheel with the W4, which is 4, actually W3, 3 vertex outside and 1 in the center is equivalent to the K4, the click with 4 vertices. So every click with at least 4 vertices that appear, we are going to find a odd wheel inside of it. So if the solver finds very bad solutions that are very dense, we're going to be able to detect them very fast and just say, okay, you have a lot of vertices, but those 4 that correspond to those 4 disks, they are already violating tricolorability. And this can be separated in polynomial time. And it's actually pretty efficient and pretty easy to do. So that is why this class is interesting. And in practice, this helps a lot. That instance that we showed before, it has K4. So we're going to iterate, giving a solution, we're going to find one of the gadgets has a K4 and add the constraint, okay, this K4 is forbidden, involving the DC and the other 3 disks. So we're going to iterate a most linear number of times. We're going to find 1 violation for each gadget, and we're done. We don't have to explore all the exponential cases. However, this is still not enough. There's no guarantee that we're not going to do this exponential behavior. So we are solving an NP-hard problem. The subproblem is also an NP-hard problem, and we even have the risk of cycling exponential number of times. And this is pretty much graph theory, but we can do better using geometry. Actually, it still works for general graphs, but we can make those wheels stronger. We can combine wheels that have the same cycle and their vertex in the center, they are connected. So we can replace this wheel for a generalized wheel that has a click in the center instead of a single vertex. And this can be done in polynomial time and make things converge a little bit faster. And this is what the constraint is going to look like. Before we had like sum over the y's on the odd cycle and a single vertex, and we have to pick at most n of them. There are n plus 1. With this lifting of the click inside, it's easy to see by case analysis that we keep the same right-hand side. So we can only pick n. We are limited by the cycle outside, but the click doesn't change that number. So we only make this constraint stronger. We have more variables on the left-hand side, and the right-hand side is still the same. And just to give an idea how this is separated, those are the vertices from the previous example of odd wheels. And here we replace the respective disks by disk with radius 2. And we have this image. And essentially, giving one of those disks of radius 2, every point that corresponds to a disk center that falls within it means that those two disks overlap. So in particular, the region that contains V, it is covered by all of those disks with radius 2. So any disk whose center falls in that face that contains V, it can be considered for that click. However, we cannot add all of them because between them, they might not overlap. So we find the points that lie within that face, and we find the maximum click among them. Since these are in these graphs, maximum click can be solved in polynomial time, but it is n to the fifth. So we do this in practice using integer programming because it's faster. But essentially, we can just, given a wheel, we construct these arrangements to test the disks that are inside that space. It can also be done efficiently using search trees, and we can just lift this and find stronger constraints. And this helps a lot, everything that we just did. Now we went from 500 points, 800 points to 2000 within the same 3K disk. We have two parameters, so it's kind of hard to explain how they grow, but now points are the bottleneck, and we went up to 2000. And if we have fewer points, we can go to hundreds of thousands of disks. And well, the master problem is only on Y variables, it's only on set cover. It has no symmetries anymore, so we don't have to care about that. Symmetries were pushed into the subproblem that is solved by a more capable technique in terms of handling symmetry. You can just turn a flag in the constraint programming solver, and it's going to handle symmetries a lot better than interlinear programming. However, we still have lazy constraints, so we cannot have the preprocessing, so it hurts performance a lot. And there's also another issue. In the beginning of search, you might find solutions that are simply too dense. They have so many disks, and we're going to separate it and say, okay, we don't pick a lot of disks in this region. But the problem is they are so far from optimal that eventually they're going to be irrelevant. So we're going to keep constraints that are simply not useful as we approach the end of solving. And combine those two issues, the master problem keeps growing. We don't have preprocessing due to lazy constraints. We still have a hard time finding feasible solutions. So to give you an idea, we start solving the master problem, set cover, perfect, find a solution, rejected, find a solution, rejected, and then it starts to grow a lot of violations, and the solver cannot find primal solutions anymore. Here, there are two things that we can do. The more natural one is, okay, let's study how to find primal feasible solutions. The decision problem is NP hard, so this is going to be an issue, but we did some of that and it helps. But more interesting, we can change our approach to implement vendor decomposition. So before we're doing search, as always, we start with just the master problem, find solutions, find cuts, find solution, find cuts. Now we're going to do differently. Instead of using lazy constraints, we're going to pretend the master problem is a final model, it is not going to change, feed it to the solver. So we have all preprocessing available, and it doesn't change until we find an optimal solution for set cover, at least in the beginning. So now we separate constraints for that set cover instance, which is much closer to an optimal solution. It doesn't have oddly dense regions. So the cuts are more meaningful because they're closer to what we actually want to cut. There are solutions that have fewer disks, but somehow are not precolorable, and we have preprocessing again, which is tremendously helpful when it comes to solving interlinear programming. And this pushes us to 5,000 points, from 2,000 to 5,000. The speed up was huge across the board. There's very few iterations. By combining those stronger cuts to avoid that could multiple solutions at the same time, looking at solutions that are close to optimal. And we got to a point that everything we tried make it worse. We couldn't, no change that we made had a positive impact. Everything is making it slower. Standard techniques from literature, nothing. We just stuck here. And instead of, bashing our heads against it and try to make it faster, the question we start to ask is, why is it so fast? Is there any geometric justification for that? Because it is converging with very few iterations, which is observing some problems, but this is something that is not usually done in the literature using decomposition, which is trying to justify why does the decomposition works. And we start to work on that direction. So it performed very well. And the idea, the intuition behind it is that we start solving a pure set cover using disks. But our goal is to solve the true colorable version of that. But it turns out that those two problems are not that different. Because you can see intuitively that, if you're trying to cover using fewer disks, you might not overlap them too much. So there is some similarity between those two problems. And this is what makes this is one of justifications. It doesn't give us a bound. We don't know if it is going to perform well always, but it gives us some intuition to justify why is it working so well. And it comes from the fact there's a very interesting property of unit disk graphs. We use omega to denote the maximum click size, and we use key to denote the chromatic number. So the smaller number of colors that you need to color a graph, omega is the maximum click that you can find in that graph. So it is straightforward that the size of your maximum click is a bound on your color. You're going to have to assign different color to each one of those vertices. But which is unique to unit disk graphs is that the upper bound is a constant. So for general graphs, we can have graphs that don't have triangles. All the clicks are at most involving two vertices, and they have arbitrarily large chromatic numbers. However, this doesn't hold for unit disks. Unit disks, there's a constant balance between the click size and the coloring number, the chromatic number. And this is a property that we are going to explore. The idea is in two steps. First, we show that, the minimum cover cannot find a click that is too much larger than any other cover. And using this, we just show that there's a constant bound. So the number of colors that our first solution found, the one that is minimum cover, it doesn't care about coloring. It is within a constant factor of the smaller amount of colors that we can use in any cover, in particular of any three-colorable graph. So if there is a three-colorable solution, this is within a constant factor of that. So essentially, of course, everything is NP hard what we're doing, but we start approximating that number. We start with a number of colors that is reasonably close. And then our cuts are going to just make this approximation better and better and better until we find a three-colorable graph if one exists. And this proof is a little bit convoluted, but the idea here is that, okay, if we look, go back to instance here, I think it's better. So given a click, here all clicks, we have a click of size 3. For any unit disk, if you look at a click, it has to share points, and the disks all have the same size. So the area that they can fill, that they can cover, is limited. And in particular, all points that this click cover is within that area. So our proof essentially shows that, okay, the points are within this area. So the most optimistic way to cover is to have disks outside of this area that touch as little as possible. And so they can only fill such a region. We find a region that has any candidates to cover that click, which is the maximum click on the minimum cover. So basically, we have a click there. It is large. It is making our bounds weak. We see, okay, what is the best that we can do? This click is making our life harder, but what is the best that we can do? And we spread the disks, and we solve a disk pack problem on that region that is a little bit convoluted. Maybe we'll have time later to discuss that. But the idea is, okay, I have this region. How many disks can I fit in this region without overlapping? And that gives us an idea. Solving this was kind of hard. We need to use we have an upper bound of 16, the maximum, just that we can think that region is 16. We can get that by solving a pack problem, writing this nonlinear problem for packing, and have some upper bounds on it, but it is so hard. There's like 15 variables, and it takes days and days and days and so many memory that we cannot finish solving it. But the idea is we construct a region, we find how many disks can fit that. In this case, our best bound is 16. And so if we can fit 16, that means that our click can be at most a 16th fraction of our original click. Multiply this by 3, we have a 48. So without going too much detail to show that, very loosely, this is not tight at all, this constant, but that we are within 48 times the number of colors in our minimal cover that we are in our best covering in terms of minimizing colors. So this gives an idea. However, this is very loose. The worst, I think, that we could do is this instance that has let me explain that. We have endpoints spread evenly across a disk of radius 2, and we want to cover that points. Each point can be covered by 2 different disks. One inner disk, so this picture looks a little bit like a flower. We have the inner disk and an outer disk. All inner disks touch, so one, and all covers have the same cardinality. If you are very unlucky, we can solve the minimal cover for this and find all inner disks. That is very unlikely to happen, but if that happens, we have all of them touch. So we have a click of size n, and we need n colors. What we can do, we can pick all the outer disks. So there is a properties of unit disk that guarantee that we should pick all the outer disks. We are going to use we are going to n over 6 times. We're going to choose exactly n over 6 colors just by picking the disks on the outside. But we can do even worse. So right now our reach is 6, but you can make it even worse. There's a way to pick n over 7 in the inner of the inner disks and 6n over 7 in the outer disks, such that this can be 7 colorable. And I cannot. It's very hard to show 7 colors, but the idea is this is the worst that we could do. It's really inspired by the proof. We have a very bad click in the middle, and there's a solution that uses all clicks as further as possible from the center, so they overlap as little as possible. And even then, the worst that we could do was 7. So we are within 7 or 48. And this leads us to our open problems. There are a couple more, but they are a little bit more geometric and require explaining other things. But essentially, can we squeeze more performance, right? We tried everything, and that's the best that we can do. This decomposition works very well. It is very tight. All improvements that we try, at least from the literature, didn't work. And of course, this constant that is between 7 and 48, we really wish to get that down to something smaller or at least tighter. And anyone has any questions? I think that is what I had to say.
Questions?
So this constant ratio of 7 that you found, this was this example that you came up, but in practice you would find something smaller?
Oh, much smaller. Yeah, we never found anything larger than 2, I guess. Even, yeah, we ran, I think, thousands of instances, and it was never larger than 2. Even for this instance, if we try every possible solution, and on average is going to find 3.5. Because this is very unlucky. If the minimal cover take everything inside. If you choose something outside, that reduces the number of colors necessary.
Did you say how you're solving the subproblems?
Yeah, the subproblems are solved first by looking for odd wheels in polynomial time. And when that fails, we use the constraint programming model. So we try to heuristically separate odd wheels. And when that fails, which is rarely ever, we look at the constraint programming and try to find a violation. We also have another technique where we split the graph in biconnected components, where we can just look for violations in smaller subgraphs. And basically that's it. We break the graph because the block tree that is obtained by shrinking biconnected components, it can't be colored knowing the coloring of each component. So if every component is recolorable, we can recolor everything. And that allows us to break the problem and solve a lot of smaller graphs in parallel.
And constraint programming would be much better than, say, mixed integer linear programming for the subproblem?
Yeah, I mean, it was never a bottleneck for us, at least not when we did like all these heuristics and splitting out the graph, but it is better because it has easier time with how symmetric it is the model. So just black box constraint programming beats black box interlinear programming for this kind of coloring. I mean, we could do a lot more engineering on the interlinear programming, but since there was never a bottleneck, we just keep constraint programming. And using that lifted wheels, we barely ever need to actually do the exact separation. At least in practice, the odd wheels appear a lot in feasible solutions.
So let's thank Allan again. Then we're taking a break, and for those who so wish, we can reconvene after 10 minutes or so for continued more technical, more informal discussions.